In this short video, I present my book, Untangling Complex Systems, a Grand Challenge for Science. Although a universally accepted formal definition of complex systems does not exist so far, I think that everybody agrees with me when I say that human beings, their societies, the world economy, the natural ecosystems, and all the living beings they embed, the climate, and the geology of our planet are instances of complex systems. Seemingly, they are pretty diverse. However, they share at least three features outlined by the interdisciplinary theory known as complexity science. First, complex systems are constituted by many elements and reciprocal relationships. Usually, they are described as networks in which we distinguish nodes that are the elements and links that represent the relationships among them. Different complex systems are usually characterized by distinct network architectures. Nodes and links are often diverse and variable in time in their behavior, and complex networks show high degrees of nonlinearity. Second, complex systems are out of equilibrium in the thermodynamic sense. If they involve just inanimate matter, their behavior depends on force fields. If they include living beings, their behavior also depends on the variable information. The living beings encode, collect, store, process, and send to pursue their goals. Third, complex systems exhibit emergent properties. A property is emergent when it belongs to the network as a whole. As proclaimed by Aristotle in his Metaphysics, the whole is something over and above its parts, and not just the sum of them all. One of the founding fathers on complexity science, Philip Anderson, declared, "The whole is not only greater but very different from the sum of the parts." In my book, I proclaim that any complex systems is like an outstanding piece of music or a brilliant work of art. If we listen to Beethoven's symphony or we look at Raphael's fresco, we can try to understand their beauties by decomposing them in their constitutive elements, which are musical notes and colors, respectively. If the single constituents are taken apart, they are not masterpieces. Only when they are organized uniquely by the musician in time or by the painter in space, musical notes and colors become attractive and give rise to masterpieces. Some emergent properties are understood and often predictable. In my book, I present many examples by showing the possibility of having temporal and spatiotemporal self-organization phenomena in ecosystems, economy, biology, chemistry, and geology. Moreover, I present instances of deterministic chaotic dynamics that give rise to fractal structures. Other emergent properties are not fully understood, and they are not predictable at all. One example is life. We don't know exactly how life emerged on Earth. We cannot obtain life from scratch, from its molecular constituents. We strive to predict the evolution of biological forms. Another example is human intelligence. Although the term is widely used by philosophers, neuroscientists, psychologists, AI researchers, its meaning is still elusive. And we don't have a widely accepted universal definition. Furthermore, we need to find out how intelligence is related to the electrochemical activity of our brain. Why are there emergent properties of complex systems which are not understood and predictable? There are at least three principal reasons that outline an epistemological complexity presented in my book. What can we do for a deeper understanding and more reliable prediction of complex systems' behaviors? First, We need interdisciplinary approaches in research and teaching. It's urgent to propose interdisciplinary courses on complex systems to the new generations. My book can be adopted as a textbook for such a course. Second, suggest, since the reductionist approach is often inappropriate for describing complex systems, it's reasonable to apply the systemic approach, which focuses on the behavior of the entire system. Or alternatively, we might use the mesoscopic approach, which focuses on the behavior of clusters of nodes and their reciprocal relationships. Since the behavior of any complex systems is highly dynamic, it's necessary to monitor this behavior continuously by collecting, storing, and processing massive data sets, the so-called big data. Furthermore, it's becoming evident that an alternative way for doing experiments on complex systems is to perform computer simulations. For these two last reasons, we must speed up our computational machines, extend their memory space, and contrive more effective algorithms. I think there are two relevant strategies to succeed in reaching this fifth goal. The first strategy consists of improving current electronic computers based on the von Neumann architectures. The pace of their improvement is described by Moore's law, stating that the number of transistors per chip doubles every 2 years, increasing computer speed and memory space at exponential rates. However, Moore's law will stop holding sooner or later because transistors will be made of a few atoms. Chips producers invest billions of dollars in contriving computing technologies that can go beyond Moore's law. The second strategy is the interdisciplinary research line of natural computing. Researchers working on natural computing draw inspiration from nature to propose new algorithms, new materials and architectures to compute, and new methodologies and models to understand complex systems. The rationale of natural computing is that any distinguishable physico-chemical state of matter and energy can be used to encode information, and every natural transformation is a kind of computation. Within natural computing, we distinguish two important research programs. In the first research program, one exploits the physico-chemical laws to make computation. Every physico-chemical law describes a causal event, and any causal event can be conceived as a computation. In fact, the causes are the inputs, the effects are the outputs, and the law governing the transformation is the algorithm of the computation. The second research program on natural computing mimics the features and performances of the natural information systems that belong to living beings. We might mimic living cells, nervous systems, immune systems, and the societies. All these systems can exploit matter and energy to encode, collect, store, process, and send information. Due to many difficulties we encounter in dealing with the epistemological complexity, do we really need to investigate complex systems? David Hilbert was used to stating, as long as a branch of science tries to face an abundance of problems, so long it's alive. A lack of problems foreshadows extinction or the cessation of independent development. Complexity science is particularly alive because it's essential when we face global challenges and we want to reach the goals listed in the 2030 agenda compiled by the United Nations. It's not by chance that the same theoretical physicist Stephen Hawking proclaimed that complexity will be the science of the 21st century. If we examine the never-ending human journey to discovering the secrets of nature, began with the appearance of humans on Earth, we might declare that it has been characterized by two revolutionary intellectual events so far. They are the birth of philosophy in the 6th century BC and the mature formulation and application of the experimental method in the 17th century AD. These two events split the entire journey into three periods, which can be called practical, philosophical, and experimental ones, respectively. Now, at the dawn of the 21st century AD, we are expecting another revolutionary intellectual event that will allow us a deeper comprehension of complex systems. If it occurs, and it has the features mentioned extensively in my book, a new period that will probably be called computational will begin. There's a lot to do before untangling complex systems. It's indeed a grand challenge for science. As the same Einstein declared, we should learn from yesterday, live for today, hope for tomorrow. The important thing is not to stop questioning. Thanks for listening and watching this video. You can find the link to my book and my papers below this video.